let's go over some of the homework first here on parametrics. And number 43, it said, consider Kevin's hit discussed in example 9, and I took the liberty of pulling up the example 9 so you have some details. Approximately how many seconds after the ball is hit does it hit the wall? Okay, so Kevin is hitting a baseball at 3 feet above the ground with an initial speed of 150 feet per second at an angle of 18 degrees with the horizontal. Will the ball clear a 20-foot wall that's 400 feet away? So the first thing I'm going to do is draw a picture here. There's the ball that Kevin is hitting, and it's 3 feet above the ground. Right, because he's swinging the bat 3 feet above the ground. And then it takes off at 150 feet per second. But anyway, how far away is the wall? The wall is 400 feet. So this is 400 feet. And they say that the wall is 20 feet high. Okay, and it's so we need the parametric equations here. So x of t is the horizontal distance, which will be its rate in the x direction, which will be 150 feet per second times the cosine of 18 degrees, and that's the coefficient. And then I put a t here because this is rate times time. This is velocity times time in the x direction. And then I can create a distance, because this is pointing as to where the ball is at some time t, correct? And so then you're going to have an x component position and a y component of position. All right, and so y is going to be the velocity in the y direction, which will be 150 sine of 18 degrees t, minus, now in the y direction, we always have gravity working against us. So that's going to be minus 16 t squared. But yet we're not starting on the ground, are we? We're starting 3 feet up, so we have to add that.
What's the initial velocity?
Yes. All right, so those are our parametric equations. And the question says approximately how many seconds after the ball is hit does the ball hit the wall? Well, how far away is the ball? Or the wall, I'm sorry. 400 feet. Now, what kind of distance is that? Horizontal or vertical?
Horizontal.
Horizontal. So I'm going to set the horizontal equal to 400. So for part A, we're going to say x of t equals 400, and that's going to be 150 cosine of 18 degrees times t. And to solve for t here, we're going to get t equals 400 over 150 cosine of 18 degrees. So somebody's going to have to do that on the calculator for me.
2.80.
Okay, 2.80. Good. And I'm going to open my calculator here so we can have fun with looking what the graph looks like in parametric equations here. And you guys said 2.80 seconds. All right, let's get the calculator up and over. And I'm going to go to y equals here, clear out my equations here, and I'm going to say in the x direction 150 times the cosine of 18 degrees times t. Now you notice the t is on the outside of the parentheses here. Okay, I'm just going to double check my mode. I am in degree mode, so make sure you're in degree mode. And then I'm gonna go down here, write the y parametrics, which is gonna be 150 times the sine of 18 degrees times t minus the 16t squared. Oops. There's the square. Plus 3, because I'm 3 off the ground. Now, I want to draw the fence. How far away is the fence? We said is 400. Is that a horizontal distance or a vertical? I'm asking it again, but it's horizontal, so I'm going to put it in the X. I'm going to put the fence at 400, and I need to make it certain height,
Oh, your computer's like,
right? I didn't step on it.
oh, that's okay.
I need to make it a certain height. I need to make it what?
4-0.
20 high. So it has to be 20 high in 2.8 seconds or 3 seconds. If I want to make it, how about 2.7 seconds? I make it 20 high. How do I make it 20 high in 2.7 seconds?
Just make the T max higher.
I'm going to say KT equals, it's 20 feet. And I want T to be 2.7. So we'll say 2.7 K equals 20. K equals 20 over 2.7. Can somebody do that math for me? Or it doesn't even matter. So my equation can be 20 over 2.7 T. That's the slope. Just to make it 20 feet high at 2.7 seconds? Yes.
Yeah, I was gonna ask, isn't it 2.8?
It's 2.8.
Yeah, we want the wall to graph.
I want the
before
wall to
ball
be at
gets
20
there.
before the ball gets there. Just to see it.
Wait, so like the ball will go over the wall, so it's.
No, I think it'll hit it. I
Did he
suspect it'll
high
hit it.
enough?
But we'll see. 2.7 times T. All right, and then let's change my window. How far horizontally? I've already got it set to 415. Will that show us the wall? The answer is yes. What about the max? Do you think it'll go 100 feet in the air if it's, you baseball players, you're hitting it
No,
150 miles per
not
hour
He hit no. He's
with
just
an
at
angle of
102.
18?
Angle of 18. It's probably going to go at 50.
All right, well, so 100 should be okay. We should see it. And you'll notice I changed my T-step to 0.1 so I can see the trajectory. So let's see what happens here. There it is. The wall is growing. Boom. I can change my window again to, instead of T-max being 5, I should make it 2.80.
That's a problem. I have a problem where my things don't graph at the same time.
Simultaneous mode. So you got to go to mode and simultaneous. You want them to graph at the same time.
Can I see your window again?
What?
Can I see your window again?
My window, sure, right here. And to get in simultaneous mode on the 89. You're gonna go to y equals, go diamond y equals, and then hit F1. Number 9, which you can't see. And you want to be not in sequential mode, but in simultaneous. Okay, so you're going to go to y equals, and then number 9 is format, the graphic format, okay? And you want to be in sequential or in simultaneous mode. Okay, that's how you do it. All right, everybody get it to graph.
Yeah.
Yes.
Yeah.
I'm having trouble with mine. It's stopping right there. Stopping.
Okay, so let's go to our window, and you want your T-max to be 2.80 because that's when it hits the wall, right? Can I say another hand over here?
Like, I don't know why we do the slope of 20 over 2.7.
I just want the wall to be 20 feet high by the time it's 2.8 or 2.7.
Oh.
That's all I did, right? I mean,
Oh, so okay.
If
So if
you
you
made it
divide by
as T-
2.7, then that by 2.7 should be 20.
right. So we could just make it 2.8. Let's make it 2.8. Let's just have some fun. So what are we going to do? We're going to divide the wall height by how long it takes to get there. Let's see. I just changed it to 20 over 2.8. So should they crash at the same time?
Yeah.
Boom. So the wall is 20 feet done at 2.8. Because what happens when T is 2.8? The 2.8's cancel in the denominator. See how that works? And it's 20 feet high. All right. That's pretty cool. We got that to work. Now, the part B says, how high up the wall does it hit? Well, what do we need to know? Yep, Josh.
When it hits the wall, and you can do.
We know when it hits the wall.
You could take y as 2.8.
Yes. Yeah, we can take y of that. Now, what's really cool about this calculator, wait till you see this, is that we can go second quit out of here. And remember, back in the day when I talked to you about that alpha F4 key, alpha F4, what do I want? I want the height, right, at 2.80. So where's the height going to be, the X1 or the Y1? So we're going to scroll down to number 2 and hit Y1 of, we're going to put parentheses in here, put what, 2.80, and it'll give you the height at 2.80. How nice is that?
Why is the book wrong?
What do they say?
Well, we estimated it
I'm sorry, that's,
100.
oh, you know what? I bet you that's the rounded answer,
I did it
2.80.
with like the exact numbers.
So let's do it exact. How would I find out what the exact is? I could say alpha F4, I want number 2, parentheses, I could say of 400 divided by parentheses 150 cosine of 18 degrees. I close the denominator. This closes the y. See how much of a difference rounding makes?
Oh my god.
I mean, yeah.
Okay, so let's not round, let's use the exact answers. Until the very end, you know what I mean? So when you're giving me the answer for the time, you can say 2.80, but when you're using it to do part B, what should you do?
Not round.
Not round to get part B. Everybody follow how I got part B? How cool is that? I'm sorry, I think that's pretty cool. Now, if you forget about the alpha F4 key, what could you do? You could say, all right, well, I know that y of t is equal to 150 sine of 18 degrees times t minus 16t squared plus 3. I could do y of 2.80 equals 100. You know what I mean? You could plug it in yourself by hand, but don't use the rounded answers. Please, oh please, oh please. Yep.
Can we also do a second trace value?
Let's see. Let's see what we can do. We're going to go back to the graph and go second trace value when t is 400. Look what I'm going to do. Divided by 150 cosine of 18. Didn't like that, did it?
You could stow the answer.
Yeah, we could.
Or
Second,
stow the time.
quit. So I'm gonna go up here, and do 400 divided by parentheses 150 cosine of 18 degrees, close. Stow alpha A. Of course, it didn't take my alpha A, did it?
It still comes up with an error.
Alpha A. So in parametric mode, it doesn't like that, does it?
No, it did it.
But when you put it on the graph, it still doesn't work.
Mine didn't like it, did yours?
No.
So what happens when we go here? We go alpha F4 and we hit number 2, parentheses. Will it let me use alpha A here? Oops, that's too many. So I don't know why it's being peculiar like that, but it works there, but all right. So question on number 43. It's not too bad. All right, yep.
How do we, I don't know if you're trying to do that, but like, how do you plug it
In the what?
to the y equation if you want to do it manually?
I mean, I would just type the numbers in my head. And I put alpha A here and I put alpha A here.
What are you supposed to
The Y, the height. Right, because the Y is how high it is. So I'm trying to find out how high it is. Yeah, right? All right, let's do number 15 really quickly. I'm going to just do part A. Because I think the rest will follow. So Nancy hits golf balls off a practice tee. Now practice tees are on the ground, right? So that right, they're not up, they're not elevated.
It's your top bill. Or
What?
baseball, it's your top bill.
Right. Right. But okay, so we're going to assume that we're on the ground. All right. And she's hitting the ball with an initial velocity of 180 feet per second with 4 different clubs. How far down the fairway does the ball hit the ground if it comes off the club, making a specified angle with the horizontal? Okay, so she's using an initial velocity of 180 feet per second. So her distance in the x direction is going to be modeled by 180 times the cosine of, because the first angle is 15, cosine of 15 degrees times time. Because this is the rate, that's the velocity times time, feet per second times seconds gives you feet. And so that's the position in the x direction. And the y is going to be 180 cosine of 15 degrees times, sine, sine. Sine of 15 degrees times t, but in the y direction, what's working on it? Gravity. So then negative 16 t squared plus how high it is off the ground, which is 0. So I'm not going to put anything there. And they want to know how far down the fairway it goes. Well, what happens once you hit a golf ball down the fairway?
Roll.
Well, it's not. It hits the ground, right? Now we're going to assume that it's not rolling.
It's a sand truck.
Right? Yeah, it goes clomp, right? It just so in this problem we have to make the assumption that once it hits the ground, it's parked.
Magic physics lanes.
Okay. So how do I find out where it hits the ground? Well, what is its height when it hits the ground?
You could plug in 0 for y to itself.
That's right. So we're going to say 0 equals 180 sine of 15 degrees times t minus 16t squared. Now, this is because it's on the ground once it lands. So we can factor this. We can say 0 equals t times 180 sine of 15 degrees minus 16t. then I can set both of these equal to 0. Well, hello, time at 0, she's on the ground. Well, of course the ball is on the ground when she's about to hit it, right? So she's on the ground when she starts, and then at the end, which will be 180 sine of 15 degrees minus 16t equals 0. So that's going to be 16t equals 180 sine of 15 degrees. So solving for t, we get 180 sine of 15 degrees. Whoops. Let's put too much like 150. 15 degrees over 16. So t is going to be, let's do that in the calculator. Clear this out. So it's going to be 180 times the sine of 15 degrees divided by 16. That's how long the ball is in the air. Do you agree? That's time. Okay, so I'm going to go to y equals, and let's model that behavior parametrically in the calculator. So what do I have to change here? This is going to be 180 times the cosine of 15 times t, and then I have to change the amplitude on this to 180, and then change this to sine of 15, and then I get rid of the plus 3. Delete. Delete. Okay, and I'm going to not worry about this because how's it going? How's the voting going?
Well, we weren't even, and now we're behind.
And for some reason, they have 2 more percentage points than they should have. Your doesn't make sense.
You're hacking the system.
Okay, so I'm just deselecting this so it won't graph that part. Okay, so I want to know that I know that the time here is what? Let's write it down. We said 2.911714257 seconds. So how do I figure out how far the ball went? Well, how far the ball went is going to be the horizontal piece, isn't it? So I want to do x of 2.911711425, right? Now, is there a way to do that on the calculator without much effort since I stuck it in y equals? F4. Alpha F4. Now, I want the x instead of the y in this case. And I'm going to go of, now I don't have to store this, I can just go up and grab it. So there it is, close parentheses. And so the ball is in the air for 2.911 seconds, and it goes 500.25 feet.
Seems a bit unrealistic.
Well, I mean, she is hitting the ball pretty hard, so.
Feet. That's pretty realistic. Because you can drive it 200 yards.
But she's bad.
Hey, at least she's trying. Right? So this is part A. So what is the strategy here? You have to first find
How
long the ball is in the air. Well, how do we know how long the ball is in the air? Well, we know when it hits the ground again. Okay? Everybody got it?
Then you plug in time for X.
Right. Okay, so what would I do for part B then?
The
The same
The
thing.
same thing except
Plug in different numbers.
20 degrees. So what do you think is going to happen? I think, for example, I think the ball is going to stay in the air longer. Don't you? 20 degrees
Yeah.
versus 15. And then if it stays in the air longer, it's going to be a farther distance. But what would be the only
Unless
thing
it's
you
too
change?
high. If it's too high,
Well, if she
The only thing I'm going to change here is do what here? This is going to be,
hit it at 75 degrees and travel the same distance.
make that what? 20? Everybody with me?
75 degrees.
I've lost you.
So if you went like this instead of this, they would land the same spot. Yeah.
So I'm going to put 20, right?
So if you hit it at 30.
So she's
at
in
one speed,
3.84 seconds
Yeah,
longer,
that's the
or
same speed.
she's longer in the air longer, the golf ball.
so it's on top.
And so then I'm gonna go to y equal to change up my equation here, and then where I see 15,
Right, you see.
I'm gonna put what? 20? And then I'm gonna second quit. And now what? I could just go up here and, or no, I can go alpha F4, and I want the X of the answer here. Goes a lot farther, right? Just for a 5-degree angle change. And so I think you guys can do C and D now. I feel pretty confident about that. This helps I have some ink here. So I'm going to make this part B, right? So this is going to be how far she went in feet, and this is how long she's in the air. Okay, very simple. All right. Thanks for letting me go over that. And now we're going to talk about something else. Whew. And now for something totally different. So you're going to need a piece of paper and those fancy graphs I handed out. Okay?
One piece of paper.
It's smaller, we're following.
You mean in the,
Yeah.
The poles. Like the poles are lined, they're not right.
They're not right. Don't let the mainstream media tell you they're wrong. They're right.
is it by 1,000 or more now?
Almost. Yeah.
Oh my goodness.
And then you should.
Don't despair. We all have after school. Right? And you guys will still help me, right?
We'll try.
All right. Introduction.
All right, so we're going to change our thinking a bit here. And the thinking, ooh, it's huge, is that we used to live in a world, or we still do live in a world, where we used to call this the XY plane, where this was X and this was Y. And if I had a point somewhere here, I would label it what? X comma Y.
We're doing Z.
No, we're not doing Z's. No, we're not going 3D. Not yet. Okay, so we have X, Y. And this is the Cartesian plane. And we would call these rectangular coordinates. And how would I describe how to get to this point, XY? I would start at this place called the origin. And then I would say, okay, we're going to go X amount in the, let's say east. We're going to go east X, and then we're going to go north Y. And that's how I would give somebody directions on how to get to that point. Well, I can also give directions in a different way. I could say, I want you to head, and I'm going to draw it. Oops. Yes, I want you to head northeast for a mile. So northeast is an angle, yes, but I have to give it a reference point. So I'm going to call the reference point, instead of the origin, it's going to be called the pole. And this is going to be something called the polar axis. And there is no y-axis in polar coordinates. Okay, so I'm going to say go northeast for a mile. So I'm going to say, okay, we're going to go from the pole northeast for a mile. So I'm saying, and then I'm describing that point using an R and a theta, aren't I, at this point? Where this is theta measured from the polar axis. Yeah.
So is that a vector?
You know, it looks like a vector, but it's not. We're describing a point in space. This is a point in space, x, y. This is a point in space, r, theta. I'm just giving you directions on how to get there. So really, I should make this dashed because they're directions. I'm describing that point as r, theta. So what is r? Well, r, by definition, is a directed distance from the pole. And theta is the directed angle measured from the pole. And think about it, if I give you any distance from the pole and any angle, could you name any point? The answer is yes. Okay,
Want to be R, for X, it would be R cosine theta, and for Y, it would be R sine theta.
yep, I'm not ready to go there quite yet. So hang on to that thought. So I have to get some polar paper here. Yeah, I want you to pull out your polar paper.
Spider web.
What? Polar bear. Let me Google polar paper here.
Can you put a picture of a polar bear on there? I'm gonna draw one.
No, I don't want that one.
Real polar bear. There you go. Like a bird.
This is my polar.
It's not polar bear.
Look at this polar bear.
I think,
Hang with
Polar
me
bear.
here for a minute.
I guess they're polar opposites.
Here we go, they're polar opposites. That's pretty good. Have to hand it to you.
Who made up the pole?
Let's see if I can actually do
What's that? What's the
All right, here we go. Let's say instead of an XY point, I want to graph each point. I have to hurry here. Oops, that's a point. R theta. And the first point I give you is going to be point P, which is 3, 5 pi over 6. Okay, so what you have in front of you is polar paper, so let's analyze it a little bit. Okay, you'll notice that between 0 and pi, just like we're used to, this would be 0 and this is pi. The upper two quadrants here are in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So they're in twelfths. So this first angle here is pi over 12 or 15 degrees. Okay? So what does that mean? That means that this is pi over 6, this is pi over 4, this is pi over 3, this is pi over 2. So the middle three are the ones that we're most familiar with. Okay? But this point says P is at radius 3, angle 5 pi over 6. Yep.
So you go to the 5 pi over 6.
So you go to radius 3 here and you swing around 5 pi over 6, which is going to be
Yeah.
right here. So that's point P. Got it? So the unique thing, though, about polars is I could have another representation of this point. What do I mean by that? I could have 3. I could start at 3 and then I could rotate negative. How far?
Negative 7 pi over 6.
Negative 7 pi over 6. And that is the same point. Now, in the rectangular universe, does that happen? No. What if I did this? Could I name this point negative 3 something? Well, what does that mean? I start on the polar axis at negative 3, and then I rotate. Oh, yes.
Negative
No.
pi over 6.
Negative, you could go negative 5, 6.
Negative pi over 6.
Oh, God.
Oh, our brains are hurting a little when I hear it. Negative 3.
Negative
11
No,
pi
11
over
pi.
6.
Positive 11. When would it be positive?
Yeah.
11 pi over 6. Yes, I felt the wheels turning.
Oh, and then we're gonna start from top and bottom.
All right, I'm going to do another point. Ready? So these are all still point P.
They're the same one.
Yes.
We also do 1, 2, 3,
All right, so I'm going to do a different color. We're going to do point Q because, you know, PQ. How about,
Can you do these on different graphs?
you can do it on different graphs. I'm just going to do it on the same one. Is that okay?
Yeah.
2, 11 pi over 6. So what do? I go out 2 on the polar axis. Yep. And then rotate to 11 pi over 6. So 2, rotate to 11 pi over 6, which will be right here. That's Q. That's funny. All right, so now this one also has 3 additional representations. Now, when I say that, I'm saying 3 additional representations between ooh. So how many representations do I really have? Infinitely many, but we're only going to stick to it. Yeah, all right, what's another one, Anna?
2 negative pi over 6.
Go out 2 and then down. Yeah, I like that one. Another, now how about the 2 negative ones?
Negative 2, 5 pi over 6.
Yep. Negative 2,
Negative 7 pi over 6.
7 pi over 6. Now we're doing that pretty fast. Maybe that's what we're doing. I'm going to copy this. trickier, right?
Sure.
So we're gonna do R. That's in radians. We all remember what a radian looks like?
Yeah.
Remember this?
Yeah.
It's like a third.
57.6 degrees roughly. Right? 1 radian, 2 radians, about 3 radians, because it's pi like this. 6 radians. Mrs. Muller, what are you doing about it? 0.28 short. Why? You're right. That's right. 6.28 is 2 pi. So I'm 0.28, almost around, okay? But where's 0.28?
No idea.
So what's pi over 12? Let's look at that. What's pi divided by 12?
I'll like do it.
Yes, it is 15 degrees. I know that.
Oh, 0.26.
It's 0.26.
Bam.
So we're gonna go 1, 2, 3, and down. Just a little bit past. No, it's gonna be a little above, isn't it?
No, you're right.
That's a little fast.
Well, because,
Yes.
That's
You want
right.
to be 0.28 short.
oh, I wanted
And that's
to,
only 0.26 short.
right, I got you.
Yeah.
So this is R.
Just bubble it big enough so that.
Right, I've got all my bases covered. I gotcha. You got it, right? So pi over 12 here is about 0.26. Okay, now another representation would be 3 negative 0.28, yes. Now our brain starts to hurt a little bit when we're doing the negatives. So I'm going to start over here, negative radius on the negative R side, and then I'm going to rotate pi minus 0.28, which is,
2.86.
yes. And then I can start at the negative, and then I can rotate pi plus 0.28, which is, so it'd be negative 3.42. So it could be tricky. Okay. All right, so what I have to do next is talk to you about something called, what I call the 4 pillars of polars. Because if you know the pillars, they won't let you down.
Have that, and a vote because of that.
No, because we always have to have a reference. And gosh, I found something online here that has how many pillars?
4.
4. Trying to get something to help you memorize things, right? Whoops.
Instead of 4, they were kind of go.
Can't have them, there are 4 pillars.
It's whatever.
You have some time to draw this?
No, you don't. Okay, so here we go. So let's go back in time here. Yes, trig never leaves our lovely minds. I have a circle with radius r. What is this point? And this is theta. R, cosine theta. R, sine theta. Okay? And so in polars, this is rectangular, xy. That point would be xy. So x is going to equal, as Josh said earlier, it's going to be x equals r cosine theta. Y equals r sine theta. Now, what does r equal in terms of x and y? Well, you have to go over this far and this far, so it would be x and y. So R equals what in terms of x and y? The square root of x squared plus y squared. And the only thing we have on here that we don't have a representation for in terms of x and y is theta. So I could say that the tangent of theta is equal to the tangent of theta is
Y over X.
y over x. Go Porter. All right, so what I'm going to do here is I'm going to put polars here. And I have 4 pillars. So I'm going to say that x equals r cosine theta, y equals r sine theta, r equals the square root of x squared plus y squared. See, this is like my visual image that helps you remember that there are 4 things. And if you know these 4 formulas, they won't let you down. Get it? Your knowledge of polars will be solid. So tangent of theta equals y over x. You have a strong foundation. You won't be let down. See? I try.
You're a jokester.
I try to be, so that it sticks with you forever. So when I say pillars of polars next year in AP Calculus, you're going to go, oh yeah, I remember those.
If we care to see it.
Right? You will. All right, here we go. Now I'm going to go to another page. And so we're going to try to translate some points. Now that's huge. I know. I don't need to make it that huge. I just don't want you to forget, right? There we go. Much smaller, much more manageable. All right, so let's say we want to convert the point to rectangular. So that means I have an r theta point and I want it to go to an xy point, right? Because we want to be able to change the language. So if I give you r theta is 2 comma pi, and if I were to graph that, that would be, I go out to, you know my circles here, out to, and then I'd rotate pi, which puts me here. Okay, now, but let's say that I'm not looking at this graph and I'm going to just use the formula, the pillars of polars. So x will equal r, which is 2 cosine of pi. Y is going to equal
2 sine.
2 sine of pi. Because this is r and this is theta. And so then this is going to be, the cosine of pi is -1, so this is -2 comma 0. So this is the point in rectangular form. Okay? Let's do another one. Let's say we have -√3 pi over 6. And remembering this is r theta, and I want to put it in rectangular form, and x equals, according to the pillars of polars, r
Negative square root of 3 cosine of pi over 6.
Yes. Comma.
Negative root 3 sine of pi over 6.
Gosh, these trig facts are never going away. What is the cosine of pi over 6?
1/2 root over 2.
No, try again. -√3 √3 over 2, comma, -√3 1/2. Right? Could you put this finger down? √3 over 2.
This is
Somebody said 1/2 √3 over 2. Okay, did you guys say it right? I'm sorry.
Oh, yes.
So what does this turn out to be? This is -3 over 2, and then
And then negative root 3 over 2.
-√3 over 2.
which is pi over 6 or negative pi.
Okay. All right, what if I want to take a point and go to polar? It takes a little bit more work.
Inverse.
That means I have an XY and I want to go to an R theta. So let's say my point is -1, 1. And I'm going to do this graphically first because you'll see it right away. This is -1, 1. There's my point. So what do I need? I need an R, which is this distance right here. What is that distance?
X squared, the square root of x squared.
R equals the square root of -1 squared plus 1 squared. So R equals √2. Do you see that? So this would be √2. And so I need this angle here.
It could be
What's alpha? You go inverse or tangent of,
y over x.
which would be -1/1. What quadrant are we in?
We're in
This is
quadrant
inverse tan.
2.
Quadrant 2. So the inverse tangent of -1.
Should be 100, isn't it?
Would it be 3 pi over 4?
80 minus 45.
3 pi over 4. Of course, could you have other manifestations of this point? The answer is yes.
I don't understand.
What?
I don't understand the manifestations of it.
Well, okay. All right, so really quickly, note if I wanted to convert √2, 3 pi over 4. Let's say I have A, R equals 3, and I want to convert that equation to rectangular form. What does R equal?
3.
No. Okay, yes, it does equal 3.
Square root
funny.
of x squared plus y.
Pillars and polars.
R equals x over 3.
Oh gosh, it's huge again.
Absolutely.
What does R equal? I'm sorry?
X squared plus y squared.
And I can square both sides. X squared plus y squared equals 9. Guess what? That's a circle of radius 3. Now, why are we doing polars? Is this is R equals 3 a nicer equation than x squared plus y squared equals 9? The answer is yeah. All right. Have a good day.
Wait, did you say have a good day?
Day.
Oh, Brian, don't go.
Okay, I'm 1,000 down plus probably.
Oh, you're like fine. No, you're like
5,000 down. So
What?
please,
Come back from that.
so please
Come back.
We had a boss going, and then
spread the word.
And this game gets so eventually.
Please. Please spread the word.
Hey, Porter,
Everyone voted blank.
He's on the